Welcome to The Explainer. Let's jump right in, shall we? Today, we're diving into the hardcore, uncompromising engineering physics of synchronous marine machines. Specifically, we're focusing on how these massive multi-ton rotors actually get their magnetic field, and why marine engineers flat out refuse to rely on outdated, dangerous mechanics to make it happen. Now, just to set the stage, let's do a super quick recap from the first part of this Explainer series. We talked about the two main machine philosophies out at sea. On one side, you've got yielding speed. Those are the asynchronous machines that literally slip behind the synchronous speed when the mechanical load ramps up. But on the flip side, you have rigid speed, synchronous machines. These guys absolutely dominate the large marine market. We're talking anywhere from 5 to 65 megavolt amperes. Why? Because their speed is totally locked to the supply frequency. I mean, they absolutely refuse to concede or change speed no matter what the load is doing.
So how exactly do they pull off that unbreakable lock? Well, the secret is a physical operating principle called synchronous torque. Basically, alternating current passes through the stator windings, and that creates a really strong, rotating magnetic field. At the same time, the rotor poles are energized with DC, or direct current. That rotating stator field just violently attracts the rotor's DC field. It generates this massive magnetic locking force that physically drags the rotor around in lockstep. Seriously, it's like having one giant magnet spinning past you, grabbing hold of another magnet, and just dragging it along for the ride.
Okay, so the rotor needs that constant DC magnetic field to lock onto the stator. But think about it. How on earth do you get continuous electrical power into a massive spinning steel? Let's look at a high-stakes scenario. Imagine a shipyard comes to you and proposes a brush-type excitation system for a brand new offshore vessel's main generator. They're telling you it has a much lower upfront cost. Sounds tempting for a massive build, right? But what's the operational risk here? Think about it for a second.
Well, if you guess total disaster, you hit the nail right on the head. The answer is unnecessary spark risk and constant brush wear. When we talk about offshore engineering, we are dealing with highly explosive atmospheres and severely restricted maintenance access. So throwing sliding, sparking contacts into that kind of environment, that is an unacceptable hazard. It's a massive, dangerous false economy on any marine vessel, and that is exactly why you will not see brushes on modern marine synchronous machines.
To get rid of those hazards completely, marine machines use a frankly brilliant engineering solution. It's a completely contact-free energy path known as brushless excitation. It goes like this. Step 1, you have an auxiliary AC exciter generator sitting right there on the spinning shaft. Step 2, its AC output passes through a rotating diode rectifier bridge. That bridge is actually shrink-fitted directly onto the rotor hub, and it converts the AC to DC right there on the fly. And finally, step 3, that DC power energizes the magnetic field on the main rotor poles. The result? No sliding contacts, no brush dust, and absolutely zero sparks. So, electrical challenge solved. But a generator rotor built for a ship isn't just meant for a calm, average day out on the water. It has to survive some serious mechanical abuse. Just to put the scale of this into perspective, a marine rotor is physically built to withstand an overspeed event of up to 120% of its rated speed, and it has to hold entirely together during that, without flying apart. And there is another hard mathematical rule of extremes we have to follow here, mostly to avoid catastrophic rotational resonance. The critical rotational speed, which is the exact frequency where vibration could literally shake the entire machine to pieces, has to sit at least 1.5 times above the nominal running speed. Think about it. If it was calculated at only, say, 1.2 times nominal, any normal speed transient during an upset condition could push the rotor dangerously close to its own resonant frequency. We have to keep normal operations safely clear of that danger zone, for sure. So how exactly do you construct a rotor that can handle a 120% overspeed and push resonance that high? Well, you make it practically indestructible using something called salient pole construction. This uses punched and stacked steel plates that are bolted super securely to a forged steel hub. It's fitted with a damper winding, and the cooling coils are physically supported by heavy-duty aluminum profiles. This specific architecture is chosen because it can absolutely resist those massive centrifugal forces and intense vibrations out at sea.
Okay, let's bring all of this together. You can see exactly how a synchronous rotor gets excited without brushes, all while maintaining those extreme mechanical limits we just talked about. First, you've got your exciter acting as the shaft-mounted AC power source. Then, you have the diode bridge shrink-fitted to the hub to rectify that power on the fly.
And finally, you've got those heavily reinforced salient poles. They are DC energized and relentlessly chasing the stator field to keep the whole system locked in step.
You know, you might have come into this explainer only knowing that two machine types existed. But now you know exactly how marine synchronous rotors generate their magnetic lock without a single sliding spark, and you know the extreme mechanical limits that define their construction. But as always, this leaves us with a fascinating and frankly hazardous question as we look towards synchronous machine operation. We built this practically indestructible, spark-free rotor, right? But what happens when invisible electrical currents silently attack the very bearings that rotor spins on? That hidden killer is something we'll be uncovering in our next explainer. Thanks for hanging out and learning with me today. I'll see you next time.